All right, so yeah, so this talk is supposed to be really, really light, and also it's 4 a.m. here, so I'm probably a little bit of. I hope I don't say anything stupid. Um, yeah, but anyway, so Morse theory is really just a very simple idea, and since we talked about topology before, so I feel like it's a very good topic to concretely see some examples and how topologists actually work on stuff and things. So, and also it kind of has to do with singularity learning theory, but I'm still reading it, so I still don't get a full picture. It feels like it's well, we would talk about that later, chat about that mostly. I don't know anything, but yeah. So basically, yeah. So my goal is very simple, just to give you guys a some hand wavy introduction of how the game of differential topology. This is how the field is called. How differential topology feels like, and hopefully we're gonna go through a little bit of calculation about the Hessian and when the sorry, when the gradient equals zero, that's a critical point, and what happens there, and local structures and everything. So that's the Morse, basically Morse lemma. And there's a little bit of computation that we can go through, and we can look at that carefully. Um, yeah, so basically, it's not very ambitious, and I might even end the talk early. Um, I mean before it went out. So okay, so yeah, so first of all, this is the thing that I really enjoy when I was undergrad. So this game of cut and paste or cut and glue. So when we do topology, actually, the idea is very concrete. We just want to play with spaces, and we just want to do all kinds of operations without breaking them. So yeah, so a large part of classical topology concerns how to iteratively construct a good topology space using simple ingredients. And that's the way we classify spaces and everything without having to fix some kind of for example, if we parameterize certain things that's a little too rigid, but we actually want to talk about in general, like how ingredients piece together. So let's look at some examples. So by this, I actually mean this triangulation thing. So I think in very early time, people try to. So if you're given a space, people try to divide them into triangles, and then can conclude something. I'm trying my best, but anyway, so basically the idea is to divide a space up into triangles, and the examples here, like if you have a band like this, you can just divide them, like you can pick four vertices and then just draw lines between them so that each piece is a triangle and they somehow glue together along the edges in certain way. And this kind of configuration will give us some idea about the topology, because I mean triangle is actually in topology usually it's kind of loosely it's defined up to homotopy, or I mean homomorphism. I mean these two you can definitely find a map to make them to be isomorphic. So yeah, so also how you decompose them is not canonical like this. Like I can just cut like that instead of this, or I can just refine it by having one more point in the middle. So these are all fine. The whole point is to decompose the space into simple ingredients like triangles. Also, if you have a sphere, we can just do this, and then we can inflate it to make it rounder on the outside. But yeah, so the idea is like this. So and then I think in more modern time, the way we cut down a space is a little bit more. I mean, triangle is still kind of very like it's a little unnecessary. Like sometimes we have to, like if you have a square, we have to cut like this. But I mean, it introduced a little bit of unnecessary cuts. So in the more modern time, I think it's more popular to use this so-called cellular decomposition. So as long as you have some cells and everything, it'd be all right. But you guys can look up the rigorous definition. But I'm going to show you some pictures. That's actually I taught this class of cut and paste surfaces in ETH Zurich. So I really enjoyed this kind of topic, and teaching it is really fun. I can actually bring I can actually bring some paper and make some models in the class and everything. So, and by the way, have you guys played this game Portal? This is a great game.
Yes.
If you're into
Amazing
if you're
game.
into topology, you have to play this. So here I'm gonna use this blue and yellow to mean the two portals. So if you have a cylinder, for example, you can just represent it in this way. So you just draw rectangle and then put a portal here, put a portal here. If you go through here, you come back from the other side, right? So that's how you represent them. And by doing this, it means this edge is glued with that edge. So you can kind of imagine actually the ends are kind of glued together. So it's topologically uh, a cylinder. Well, it's actually the surface of the cylinder. It's probably not a very. It's like a scroll. Anyway, so you guys know what I mean. It's really just this thing, but it's hollow inside. We don't feel it. It's really just the surface. Um, yeah, and also there's this torus. So for torus, you can simply just draw a rectangle and then put a portal here and match it with something down here, and put a portal here, match it with something down to the right. But make sure don't mix them up. Like these two are different portals. You can't just go through from the other side. So you have to make sure they match. So by doing this, the effect is like if you have a particle that goes in this way, it will come out that way. If the particle goes in this way, it will come out that way. Also, the orientations are preserved. It's like if a guy just walk into this portal like this, it will walk out of it the same way, like before. It's not gonna walk out like the other way, the upside down. So that's also another thing about the portal. But anyway, so the whole point is that the these two are glued together. These two are glued together, and you can kind of try to imagine it in your head, like how this is homomorphic to a torus. So you can ask yourself whether you can see it, and and then just playing with this mind game is actually really fun. Okay, so here are some questions for you guys. So what about this guy? Can anybody answer this question? Yeah, I saw someone just came in. So it's just let me repeat the game here. So I'm basically playing Portal on 2D space. I'm gonna have some a piece of paper. I'm gonna put a one-dimensional portal and then match it up with something on the other side. So like blue and yellow. If you go in this way, it come out that way. And this one, we glue these two lines together to form a cylinder shape. And for torus, is like we glue up and down, left and right, and you can kind of imagine how things get wrapped up into a donut. So here I'm just asking if I put a portal like this. Yeah. So the orientations are different,
It's a
which
Mobius
means
strip,
if
right?
sorry? Yes,
It's a
exactly, exactly. That's a Mobius strip. Yeah. So exactly because we glued it the other way. Let's see. Okay, I think I'm supposed to draw it like this. Oops. Yep. So yeah, because we glued the other way, like things are um, glued. I mean, yeah, the unit interval need to be flipped before glued. And what about this guy?
I know this one,
Possibility
but
that you guys
it's because I know it already. But I'll let other people try.
you know this already. Yeah, just think about it. It's a very interesting mind game. And these are easy ones. There's some really crazy ones, but I don't want to. uh, I mean, these are those that have names. There are some crazy ones that without proper names. So.
Would this then be a Klein bottle? If
Yes,
you.
exactly.
Okay, cool.
Yes. Yeah. So
I
yeah.
think
So
if you
the
flip
way
the other arrow,
I
it's
want to see you draw this one. I want to see your sketch of the Klein bottle.
okay, yeah, let's see. So basically, the idea is you glue this up and down first, and then for these two circles, you try to just oh crap, I'm gonna. All right, how do I do this? Okay, I don't know how to draw this. But you can kind of see, like if we just transport this to this other side, we get these donuts. But if we have to twist it like that, like this. Like here we have to twist it. Oops. Every time just yeah. Okay, if we have to twist it like this, it's yeah. So let me see if I can draw. Okay, so I'm not prepared for drawing this one, but it's a fun exercise. If I can't, I would just give up. um, let's see. Okay, so let me do this first. Let me start with stars and then maybe go from there. It's not really glued, but then I want to stretch the inside. So this means I kind of want to, oops, then, oops, oh no, yeah, kind of, and then, okay, no, well, no, actually not like this. I want to go inside on the other, do this. Actually wanted to go inside on this from the side. I never had to draw this thing actually. So yeah, okay. So I think I got it. It's kind of like this. Yeah. So basically, we have to go in from the side in order to glue it the other way, the flipped way. So that's roughly the picture. I can make it better, but I think it kind of serves the purpose. All right, great. So if you guys have questions, just ask because we have plenty of time today. It's basically just drawing and do all this yoga. It's less rigorous. And also, what about this thing? I mean, maybe you guys don't know very much about the name of this object, but you can try to imagine what it looks like. So this is very weird because these two things are flipped, but you only have two vertices. It's like if the two portals are aligned like this, then this is a sphere. So you're just doing a dumpling. Just cut a just cut just um just cut up a sphere and flatten it. So this one is like you have to flip it the other way. So I don't know if any of you have any ideas, but I'll tell you in a moment.
Is it like something like a projective sphere or something? Some kind of projective space?
Yes, yes, this is a real projective. So I think this is RP2. I've been dealing with complex number for okay RP2. So this is a real projective surface. Um, I mean, that's the definition. So there's really no way to see that. And also this thing, just like Klein bottle, it cannot be embedded into 3D three-dimensional space. So I can't draw it. But I can sort of draw it because there's another way to represent this space. This space is actually now. Let's take a step back. We let's look at Mobius band. So what is the boundary of Mobius band? The boundary is this thing, right? I mean, if you know manifold with boundary, just look at anyway. So I'm really talking about its boundary. So you know that the boundary is just a circle that wrapped around um, that got wrapped around twice, right? So instead of cylinder has two separate circles on the top and on the bottom. But this Mobius band only has one single boundary, and it's connected. Is just a 2-to-1 cover of a circle. It's still a circle S1. So what happens if we pick a unit disk? Because the boundary of unit disk is also S1, right? So for S1 and S1, you can glue them together. Even if it means that we have to wrap it like wrap it twice, we can still glue it, right? Topologically. So basically, if you glue a unit disk uh, uh, on this Mobius band, you'll get RP2 as well. And it's almost impossible to draw it. But you can kind of imagine this is the best description I can get to. I mean, because you can almost draw it, except in the middle. It's like it's like you try to fill in. I don't even know how to say it, but this is the closest description I can get. If you want to visualize it
Wait,
as well as possible. Yeah, go ahead.
so is it's like the real plane but with only 2 points at infinity, or like I
Mm, yeah. So that's let me see. Um, that's no, not 2 points at infinity. I think you have. Let me see. So for that description, um, so let me see how to
like I
say
guess,
this.
if
Hmm?
I'm like familiar with like,
Mhm.
the like 1 point compactification of R, like that, my understanding
Uh-huh.
is that is like just the like real projective
Oh, I see.
like RP1. And then if you do
Uh-huh.
it a second, would it be like a would it be like the homomorphism from like the top half of the two sphere to the plane, or
So yeah, I see. Right. So what you're describing is like this 1 point of compactification of the planes, like somehow just wrap everything all the way to here. So what you eventually get is a sphere.
mm,
So you can kind of see this is a sphere because you just close it up by gluing it in this
hmm
kind of impossible way. But for the real projective space, it's the infinity is actually. So this is also an example that tells you that there are more ways to compactify space than 1 point compactification. So
okay,
let me erase those drawings here. So basically, one way to describe this using compactification point of view is to look at. So we have this real plane, and we're actually so at the infinity, what happens? What happens is that you just randomly draw a line, and then we consider the equivalence class of the line. And each equivalence class of the line corresponds to a point at infinity. So it's like if we got a point um, uh, in this finite space, it's fine, but it can go in some kind of cursed way, but eventually go towards one direction. So there's eventually this limit direction, and that limit direction will correspond to a point at infinity, and it's represented by this limit line. So if you go towards the other side, that will end up at the same point. So at infinity, it's like S1 circle, right? So but the two ends are identified. Does that kind of make sense? So
yeah, I think so. That this
here,
is actually this is a helpful picture.
uh-huh.
Okay,
So actually,
yeah,
from here in the original picture here, you can draw these two lines and pick an origin in the middle. Oops, let me just draw it again. Somehow just right. So let me just draw this previous one again. So you can actually pick an origin here in the middle, and you can see what I mean by identify the two ends, because you can draw a line. You can draw a line because the portal is kind of identified in this opposite way. This point is identified with that point. So that means if you have a particle that goes this way and the particle goes that way, they end up at the same point. So these two
gotcha.
actually line together very well. So
Okay, cool. Yeah,
yeah,
thank you.
yeah. So this is also an example of a space that's not orientable, but it's not something we're going to talk about today. Anyway, all right. Mm, okay. Yeah. So yeah, that these are some examples. So there's some more like cursed examples. Like I can give you. I mean, I won't give you definitive answers because they're really cursed. You can have like you can start with something like this, and then you can try to identify like you can do this. I'm just randomly drawing stuff. I don't even know the answer honestly. And you can do like yeah, let's make it orientable, and then there's this force. Let me just do IVOs. Okay, let me just do four arrows. Okay, I don't even know what I'm drawing here, but you can start with something like this, and you can have multiple edges, but identify them in some kind of random ways, and eventually it forms a surface that's really, really, really weird. And this leads to a topic of surface classifications. So I think that this one is probably eventually It's going to depends on whether this is orientable or not, and if it's orientable, eventually it's going to be one of those multi-donuts. So how many holes? That's some other questions you have to figure out. And actually, it's easy to figure out by this configuration, but it's going to lead to a lot of discussions, and I won't have time to cover all these. But this is a really cool topic because this also has to do with group theory. Because for it has to do with fundamental group of a surface. Because you can think of an arrow as an abstract element. Like if you get you can associate an arrow with a symbol G and G times G, and here's like H times H, and I times I, and W times. If these two are different directions, they're kind of opposite to each other. You can what you can do. Oops, actually, I messed it up. Just want to give you a flavor, so it's not something I really want to talk about. So G there's the same direction, H same direction, W, and then let's say I'm gonna put J here. This is 4. These two goes together. Yeah. So that was the previous one. And these two are opposites. So I'm going to put J inverse here. And W is like opposite. So it's going to be a W inverse here. So it's like you can construct a free group they're generated by all these symbols. And then you can just line them up, go around and put them together. G times H, W, J inverse, W inverse. And that gives you a word. And you have this free group this relation that will give you something. That will be a fundamental group of the surface. But anyway, I'm just giving you a very quick outlook, like what lies ahead. So this is also another very interesting thing to talk about, but won't talk about it today. But anyway, so as you can see, the point I want to make here is that people, topologists, tend to cut up a space into simple stuff. So here we no longer use triangles. That means we have we have less waste. We can just start with a rectangle and gluing things together. And then decomposition comes in when we pick, for example, here we pick a vertex that's a zero-dimensional component. And if we have an edge, and that's a one-dimensional component, and usually we have at least one surface that's kind of glued together, that kind of glued to all these edges. But you can have multiple. Like you can have two rectangles, and you can glue this edge with that edge, this edge with that edge. That's also fine. Then you will have a face and another face, F1 and F2 and things like that. So yeah, so it all comes down to breaking things down into simple pieces. All right, so these are examples, and then in this classical topology, there's this notion called Euler characteristics. So if you remember the formula, it's basically the number of vertices minus the number of edges plus the number of faces. And in high school, I think when I was in high school, teachers already taught that, and I didn't even know why it's so important. It's just a number. We just sum it up like that. Um, but actually, the whole point of defining such a thing is to say that this number is a number that can be associated the to the homomorphism class of the space. Like no matter how you twist it, no matter how you divide it, it all ends up being the same number. And that's an important feature. So like the pathway from the classical geometry to modern geometry is one of the biggest difference is that there's the idea of invariance. So people no longer focus on like constructing complicated stuff, but rather they focus on what is invariant under complicated operations. So here's the same thing. Like we can divide the space any way we want, but if we have a number that's unchanged, no matter how we divide it, and it's only dependent on the topology type, which is the homomorphism class, and this is important number. So yeah. So anyway, okay. So let's do some examples. So for example, here we have this sphere. This is the triangulation of a sphere. So just you just need to inflate it to make it a sphere like, but as long as you know it's a sphere. So for this thing, we can compute. So how many vertices there are? So there are 4. So we put 4 here, and we have 6 edges. So we just put a 6 here, and we have 4 faces. So we plus 4. And right. So let me get rid of those. Okay, so yeah, so and then you get a number 2. So you can divide it up in another way, or you can add a vertex inside, and then you can do something like this, connect them, do anything you like. Eventually, you end up with the same number 2. So that's an important observation, and it's a number that's about the sphere itself. And now, what about this space? And this is what we just did. This is cellular decomposition. No longer about triangles. So in this case, we can do the same thing. We have 2 vertices, so we have a 2 here, and we have actually this is just one line because these 2 guys are glued together into one. So by drawing these two edges, we actually only have one single edge on the space. So we only put down 1, and we have one surface that sits in the middle. So that's 1 here. If we do the calculation, it ends up having 2 as the answer. And this suggests, this is not a proof, this suggests that these 2 might be the same space. It turns out they are, even though we represent them differently. And what about this cursed one? Now we know the answer. This is the real projective surface. So in this case, if we do the same calculation, we end up noticing that these 2 vertices are the same vertex because how they're glued, like they glued the opposite way. So if we let the point approach these vertices, you will realize they are actually the same point. So we are actually starting with one single point in the space, but they're just drawn as 2. And then again, these 2 edges are also glued together. Even though they're flipped, they are glued. So it's just one single edge. Oops, sorry. And then again, one face, one surface sits in the middle. So if we do the computation, we know the answer is 1 instead of 2. So this we can answer definitively that this is totally different from this space, totally different from that space. It's absolutely not a sphere. So mostly invariants are used when we want to say something is definitely not something else. And it's really, really useful. But anyway, so yeah, the point I want to make is that we have this alternative sum, and this kind of very useful in topology and things like that. And we can try some others if we. I see it's been half an hour, so maybe let's go through everything. But computing disorder characteristics is actually pretty fun, so we can do it for all of them and just see what's going on. Yeah, leave it some space, but I want to go through everything first because we still have 10 pages to go. Okay, so the takeaway from here is that so topologists tend to decompose manifolds into unit disks. So if you remember all those ingredients we talk about, the vertices are simply zero-dimensional disks, right? So edges are just one-dimensional disks. They're unit intervals. The faces are just two-dimensional disks. And actually, you can go to higher dimensions. For example, for this guy, you can fill it in. You can have this, you can have this solid sphere sits inside, and that's glued to all these 4 faces. So that's a 3-dimensional cellular decomposition. You can do all these. You can go to as high dimension as you want and do whatever you want. The whole point is that we want to decompose them into disks, no matter whether you do triangulations or more modern cellular decomposition. And then there's this Euler characteristic, which is the alternating sum of them, and this is invariant on the homeomorphism. So yeah, so that's the takeaway for you guys. Okay, so now the interesting thing about Morse theory is that it connects all those previous topology stuff with gradient flow. All right, so now given a differentiable sum, I mean, if you don't know what differentiable sum manifold is, all right, because it's just a space. In this whole talk is not going to be rigorous. But when I give you a theorem, I want to give it as precisely as possible. So given a differentiable submanifold X that sits inside a Euclidean space Rn, a differentiable function f that maps S to the real numbers R. So it induces a gradient flow, And the gradient flow is defined. I mean, we are machine learning people, so we know what it is about. So basically, it's like we have this differential. So pick any vector on the tangent space, and the differential acting on the vector space is the same as doing the dot product of the gradient vector with the vector. And this dot product, if you expand everything, it's basically just taking the differential of the function and do the transpose. If you write down everything into coordinates. So yeah, it's just a good old gradient. And we have this notion of critical points. That's just when the gradients vanish. And that's basically how this gradient descent is looking for. But unfortunately, a lot of them are just like saddle points. It can go down further. But if we do a perfect gradient descent without any optimizers, it probably just end up somewhere here. All right, so I want to draw some examples to demonstrate what it looks like. So basically, the Morse theory is about the topology near critical points. Um, and then this behavior near critical points will have a connection back to the topology that we talked about in previous slides. Okay, so I want to give you a giant picture just to show you how it looks like, and it will become very important later on. So we have this big torus that's embedded into, so we have this torus embedded into R3, the three-dimensional space, and we have this natural function f given by the height of the torus, and we want to do the gradient descent to find the lowest point here. So we start from the highest point, and if we go along with the gradient, we will be able to draw those lines that I have here in the picture. So you see these lines of different color, they are gradient flows. It's like if we pick, if we pick a point here and then we just take the gradient vector and actually move it along the vector, we will be able to draw the line like that. So it's like we pick a point and we integrate the vector field. We'll be able to actually find the exact curve that I'm drawing here. So what I want to show you are 4 pictures. So I have 4 pictures about the gradient flows near critical points, and they correspond to these 4. We have one at the top, one here, and the one at the very bottom. So these 4 are gonna look like these if we zoom in. So this one corresponds to the one on the very top. So all those gradient lines will go downwards. No matter which direction you go, it always go down. It's like it's always going to be fine if you do gradient descent from the very 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 top. So and locally the function up to a coordinate change is going to look like this: minus x1 squared minus x2 squared. Maybe we shift it by a constant. It depends on how your function aligns. But really, the constant is not that important. But this is like a local representation of this critical point of the manifold of the function near the critical point. So then what about we go down one level? If we look at things here, then we have this purple circle that kind of converges towards here, and then we have this blue one that goes further down. So that's definitely a saddle point. So how it looks like is this. So if we go down, so if we go up or down, goes further down, but there are 2 flows coming from the top. They're pink, purple. So now if we complete the picture, the flows nearby are gonna be like this. Like this one goes out, this one goes in, and then nearby should go kind of towards the middle, but then goes away, diverge like that. So this is how the saddle point looks near the critical point, and a function that kind of represent that is going to be x1 squared minus x2 squared. And then if we go down one more level, it's going to look like this, because this blue guy is eventually go down here. So if we follow the blue guy, they're going to converge to the second level critical point, and we can go further down through this blue line here, and outside is just gonna just fill the picture. You get this yellow lines. And locally the function will be like this. It's gonna be minus x1 squared plus x2 squared. You can kind of check that easily, like just restrict x1 to be 0, and then you see x2 squared, and you can kind of check when x2 goes up, the value should go higher or something. So yeah, anyway. And then the very bottom, no matter where you come from, eventually will converge to this final critical point. And the function will be just x1 squared plus x2 squared. Okay, so yeah, these are the three really nice functions that kind of describes the local behavior of the function that we're given. Yeah, so just want to show you how this looks like here, and why this is related to Morse theory. We'll see that later. Okay, so and then there's this notion called Hessian, and Hessian is like given a local coordinate from Rm to R. Hessians are just defined by the second order derivatives. And we have to form them into a matrix. So Hessian is usually a matrix. So this is definition. And this notion depends on units, right? So if you do a change of variables of x, everything changes. So Hessian by itself is not like a good notion. Like in maths, we usually talk about tensors. Tensors like invariant under change of variables and everything. But here, it actually does depend on the coordinate we choose. So it's not a good thing. However, if we are looking at Hessian at the critical point, the Jacobian matrix will act on it like we put the Jacobian in the front and put its transpose at the back. So I actually forget how it's called. What's the name? Because I learned all this stuff in China. But anyway, this thing to make it a sandwich, and then we get a new matrix. So if the point we're looking at is good enough, is a critical point, the action of change of variable is actually very simple. It's just represented by this thing. Um, and this, in another word, this is an invariant symmetric bilinear form. And also, in a fancier word, this is actually a 2-0 tensor, and covariant, two covariant. I don't remember, but anyway, so this is the real meaning of tensor. Because usually, math people, physics people, usually laugh at the term tensor. Actually, tensor really means something that's independent, something that has a very very nice way when you change variables instead of just a multidimensional matrix. But anyway, so the point I want to make is that the Hessian, this second order derivatives of a function at the critical point, the change of variable impacts in a very very controlled way, like this thing. So, and this is, if you study linear algebra, probably you're probably familiar with this, because we have this conjugation, we have a conjugated by like orthonormal groups, or and this thing is like a coordinate change when we are given a bilinear form, and these all have normal forms. So yeah, okay. So just to show you, just to convince you that I'm not bullshitting, this statement here can be computed like this. I mean, we have to compute something in math talk, otherwise it's kind of. So if there's a change of variable, yi goes from the original xi, and we do this change of variable by adopting Einstein summation convention. So if we have the one of the entry of Hessian, what we're going to do is to write it down using the um, uh, yeah, was second order derivative of f with respect to the x variables, but then we can write it into y variable, and then this chain rule, Potter rule, whatever, all this kind of elementary calculus stuff. So if you do this if you do this chain rule, you can oops, what I'm doing. So yeah, so basically you just apply those calculus, and then you have to take a partial derivative of a product, and then you end up with two terms. You take derivative of this guy times that guy, or this guy times the derivative of that guy. So you have two terms, and if you expand all the calculations, again, I have Einstein summation here, which means this. Oh, I hate this. Let me just erase this thing. Okay, that means if we have this two, that means there's a sum over I prime. So I just omit it, and here y j prime and sum with j prime. Yeah, you just do this calculation, you end up with those stuff. And the condition of critical point happens when you set this term to be 0, and then you realize this thing is just acting the Jacobian matrix on the Hessian matrix by put something on the front and it's conjugate on the back. Anyway, so this is the only math part in this talk. Okay, so now the whole point is that so let's take a step back and think about linear algebra. If we're given a matrix M, what are unchanged under this equivalence relation JMJ transpose for non-degenerate J's? So we can easily conclude there's two things. One is the rank, and the other one is the index. So actually, what happens is that for matrix up to this equivalence relation, we have a normal form that's going to look like this. We have a 0. That's the degenerate part, and then we can have a diagonal matrix of identity for ones, and have another diagonal matrix of minus ones, and the rank will be just the two parts, and the index is just this negative definite part. So, right, so that's this page. Okay, so now all these things are gonna come together. If we have a Morse function, so Morse functions are defined. And the setup is the same as before. We have a differentiable manifold X embedded into some kind of very large Euclidean space, and we have a function, differentiable function that maps X to R. And usually it's like a height function if we want to draw the picture. So Morse function will be such a function that the Hessian at any critical point is non-degenerate, which means the rank is maximal. So rank, we just don't have these guys. And the Morse lemma is a very simple thing. It just says, okay, given Morse function, if the Hessian is non-degenerate at all the critical points, then actually we can write down the local structure of the function very easily as this kind of normal form. It's basically about normal forms. Like up to a tangent variable, we can really write it down, write down f into like plus minus a coordinate square, and we just do all of them. And then how many minus sign, how many plus sign will depend on this index thing. So this will happen in general as long as you pick a Morse function. So the takeaway here is just that if x and f, so if x and f are, so if f is a Morse function, then f can be easily described near the critical point, and it's fully determined by the index. Okay, so let's summarize everything. What's a well, actually, no, actually, okay. So I'm going to tell you what's the point here. So given any submanifold X embedded into Rn, so this is something I didn't talk about, but you should take it as a fact. You can find it in all those textbooks. So if you're given any submanifold X, there's always a Morse function. That's why we're doing all this about Morse function. So once we have this fact, basically, all I have been saying is that pick any submanifold. If we want to get a precise definition around the critical points, we just pick any Morse function because they always exist. And how to construct them is by those perturbation and everything. So if you experience those partition of unity and all this stuff, there's some techniques. Okay, so the second thing I want to make after this point is that the Morse function is important, and the local description of Morse function is important because the gradient flow along a Morse function will induce a decomposition. Just recording in the very beginning of the talk, we try to decompose this topologic space into unit disks of different dimensions. So here we are actually going to do the same thing. So the gradient flow of Morse function will induce the decomposition of X, which unveils its topological properties. And let me give you some examples. I'm not going to write down a very rigorous theorem because it's all the gluings. These are kind of hard to do, but they're in the textbooks. But let me try to convince you by drawing those stuff. So let's start with a sphere, and we just use the height function. This height function will be our Morse function, and the critical points are on the top and on the bottom, and we have those flows like that. So oops, spoiler, but okay. Yeah, so we have those flow lines. So how do we decompose them? Basically, if we the first bound the first critical point by a circle, and then try to extend this circle along the flow. You see, you should think of this as some kind of movement. Through time, it just gets larger and larger. They just flow along it. What we are doing is to first start with a two-dimensional disk like this, to bound the first critical point by a circle. And then by going along the flow, we're trying to attach a disk to this zero-dimensional disk, which is the second critical point here. Oops. Okay, so yeah, so that's what we're doing. That's one very, very simple example, and it's probably not convincing enough. And let's look at this croissant. So this thing, this is a sphere as well, but the height function will have four critical points, two on the top, one in the middle, and one on the bottom. So if we start to bound the first two critical points by S1, we start with two-dimensional disks, right? And then if we go along with the flow according to the picture, what we have is like we start here and then move along, move, start here, move, and they eventually meet in the middle, and they are glued along this circle, right? Hopefully, you can imagine that kind of things. So what happens is that we start with two unit disks, and then we go along the flow to glue it along a common S1. By doing this, we form a sphere, and this decomposition corresponds to this particular Morse function. And these two decompositions are different, but the underlying spaces are totally the same. Okay, so yeah, so two-dimensional disk, one-dimensional disk, and zero-dimensional disk. So, and then there's another one, more difficult one, and hopefully this drawing is good enough. So if we're given this torus and still use the height function, then we start with this critical point, and then we bound it by a circle, and then if we go down um, along this flow, we kind of realize it's actually squeezed like this. So so this is the two-dimensional part, but the one-dimensional part we already have this flow that goes down, right? So for the second, for this critical point, we can already go down to form a circle like this, and this flow line to form a circle like this. And then on the very top, we just bound it by a circle and then flow along. And then you see eventually, the boundary will actually attach to this whole. So actually, the proper way to construct this is to do it iteratively. It's like we first start with just vertices, zero-dimensional guys, and then we look at the flow. We look at the index at those critical points to form those one-dimensional cells, and then we start with the two-dimensional cell by finding one with index 2, and then we can see there's only one critical point like this, and then we go along the flow, and this two-dimensional disk will be attached to this one skeleton in this kind of weird way. But hopefully, this picture is kind of self-explanatory. but yeah, that's the idea. Basically, you start. I mean, if you have a higher dimensional space, now is the time to do a three-dimensional flow. If the dimension is higher, right? So in general, what happens is that locally near the critical point, the picture is going to look like this. It's like we're going to have index I, and high dimension. I mean, this is a cartoon really. It's two-dimensional, but it's actually I try to combine those axes into just one single axis. So there are these axes whose coefficients are, just remember this expression. It's like there are a bunch with minus sign in the front, there are a bunch with plus sign, like I plus one. There are a bunch with plus sign in the front. So I merge those coordinates together, merge those coordinates together. So it's like for this Ri guy, these are all the coordinates that goes out, and the Rm minus I guys are coordinates that goes in, that flows inward. And this, if we try to bound the disk, try to see what's actually flowing down, it's actually, this, if we just cut it off, um, it's very hard to explain this high dimensional object. But basically, what I'm trying to say is that if you see what's flowing down, it's always, you can always make it a unit disk bounded by a sphere Si minus one. And then by going along the flow, you can always attach to some kind of lower levels. And by doing this iteratively, eventually you decompose the manifold in a systematic way that you can describe. And this is associated to this particular Morse function. And it's constructed by the gradient flow. So that's the whole point. And I hope this cartoon is kind of makes sense.
Is it
Yeah, I just want to say.
associated to
Mhm.
this decomposition is unique to a specific Morse function, but if I chose a
Right,
different Morse function, I might get a different
right,
decomposition?
right, exactly. Just like these two examples, because you can see this as two different Morse functions. It looks like two different spaces, but it's actually different ways to align them. So its functions are different. But anyway, yeah. So you're totally correct. So yeah, the takeaway is really just that. Um, yeah. So what I talked about was really just that one Morse function will give you a cellular decomposition into unit disks of various dimensions. And then the takeaway of Moore's lemma is really saying that the index at a critical point will tell you how this decomposition is going to happen. Like what's the dimension of the disk you're going to put on this critical point P. So if you have index I at P, you're supposed to construct such a unit disk and then flow it down the gradient flow lines. And by doing this, you're attaching a disk di at P. And if you look at it this way, it also says that the Euler characteristics can be computed by the alternating sum of the counts of different indices. So this is something that I will show you the paper. I mean, I will send the link later in the channel. But yeah, I just don't want to write it out. But basically, the whole thing is that given Morse function complement manifold, you just count the number of critical points and then do the alternating sum. Then you can get the Euler characteristic of M by just doing all those analytic stuff without going into this hand waving discussions or anything. So this is a very concrete way of computing order characteristics, and it's still independent of the Morse function and everything. I mean, the alternate sum. Okay, so yeah, that's pretty much the content of Morse theory. I mean, it's like a what, the 10,000 feet kind of view of the Morse theory, and but my hope is really just that you guys remember this story. And there's this story. Given Morse function, you get all this stuff, and the local structure. You can describe them explicitly. That's it. That's really it about this talk. And this is one last slide about all the information, keywords, and everything. So I just want to say a few words about the case when the Hessian degenerates. So when the Hessian degenerates, I draw a cartoon here. Basically, the critical points altogether will no longer be isolated like previous examples. They will form a critical submanifold. And actually, if we think of the function being discussed here as a loss function in machine learning, it's actually a loss value, just like this. So actually, almost all the time, it's going to be like this. I think there's some proofs that we always get non-isolated critical points. And in that case, Morse theory is generalized into Morse bot theory. And that's actually very interesting. I remember it was like the story goes like if you have a manifold X and if you have Lie group G acting on this X, and then if you have a G invariant function, um, then almost always not a Morse function. But you can still talk about something similar, and you can also like try to make sense of it, and that's more spot theory and doing some group cohomology thing. And there are a lot of stuff that I don't even remember myself. But that's very interesting thing here, and it's mostly about it's just that um, it's just that the whole theory is easier to describe when you have a group acting on manifold, but it really doesn't have to. And there's this singular learning theory and this Morse theory when the critical points are isolated. They call it the regular model. And then they kind of emphasize that actually almost all the interesting models are singular models and blah, blah, blah. So they correspond to the case when the critical points forms a family, forms some kind of a submanifolds. And there is another theory out there. And it's not about topology, of course. Yeah, so and then non-degeneration, degeneration, and everything. So just to give you some keywords. And also there's an infinite dimensional version where the functions are replaced by functionals, if I remember correctly. And the space under discussion is actually a space of all functions of some probably some Hilbert space. And there's this thing called Floor theory, and that's this is a big deal. This is a big deal, especially in symplectic geometry. So this is another very cool thing. Is also very hard to navigate because you have to generalize all the notions to infinite dimensional, and that's there are a lot of open problems here. I don't even. I mean, I'm still. Sometimes it just my research kind of touches those topics, and I was always intimidated by literature on floor theory. But anyway, here just to give you a keyword. If you're interested, you can look it up. Okay, so yeah, that's all my talk. Oh, so that's exactly on time. All right, that's it. If you have any questions, just let me know.
Well, thanks a lot. This was really nice.
Thank you.
Yeah, no, this was so awesome, and I loved your drawings. Like, and yeah, I don't know, just the pedagogy of all this was great. So thank you so much.
I'll send
Yeah.
this in the channel. Right,
Yeah,
the
one thing
PDF.
is that maybe the yellow is a bit hard to see on the
Oh yeah,
white
that's true.
background.
But yeah, I have limited choices of colors.
I think orange
I can
might
make my
work
own.
better, but yeah, it was sometimes hard to see
Yeah,
exactly what.
right. I should make it darker actually. Anyway, yeah. Mm, yeah, I would make it into a PDF and send it to the channel and see.
Yeah, that's awesome.
Any questions or?
I mean, I do have more question about Morse bot theory, but maybe someone else has another question before that.
Uh, yeah, I will see if I can answer. I'm not sure. Go ahead. What's the question?
Yeah, sure. So, if we think of Morse bot theory in the machine learning world, like let's say we have a neural network with parameters. Usually, the parameters we can assume they're bounded. So we did the space we were working with is some kind of sphere. So like
Right.
the actual topology of the parameter space of a model is not so interesting. So in that case, we have this non-Morse function. What do we learn about the topology, or what exactly do we get out of it?
Uh, so what did you say? Sentence was breaking somehow.
Sorry?
Sorry, what's your question?
Okay. So
The internet was kind of breaking up.
yeah, okay.
I didn't hear your full question.
Yeah, sure. Okay, so at least for a machine learning model, the actual manifold we're working with is a sphere.
Right. Yeah, yeah.
And
It's
so
just you play a space. Yeah.
and so when we do this Morse bot theory on these
Oh,
non-Morse functions, what do
right.
we actually learn?
Right. So, yeah. So, I think, so I don't think we're gonna tell the same story here. If you wanted to have any applications on machine learning, we're not gonna talk about the topology of the space because space is kind of boring. But that's actually also like it's kind of okay. Like, there's something I didn't talk about. This generalized Poincare conjecture. It's like if you start with a sphere, you start with something that you know is a sphere, is a topology sphere, it's a topological sphere, and then you want to say something. Then then the game is different. It's like if you're given a Morse function, you already know. For example, this alternating sum. Uh, yeah. Well, where was it? Anyway, this alternating sum of the Hessian index of Hessian and critical points, they are a predetermined number. You already know it. And then the game is like you use it as a condition, and then this condition will constrain how those critical points will behave. It's like it's not just you grab any function. You can have all kinds of arbitrary index and arbitrary set of index anywhere. There are constraints, and what these constraints tell you. So the game is like completely backwards. And in the case of neural network, the parameter space is actually Euclidean space. There's really not nothing we care about in terms of the topology. So I think that if we want to apply it, it's definitely going to go backwards. It's like given that this is a Euclidean space, what can we tell about the structures near those critical points or critical locus? So sometimes it could be fruitful. It can lead to some results. But more sports theory is really not about this. It's like actually I don't even remember clearly. Uh, I don't think this. See, I don't even remember what's the condition. Okay, so I'll probably not talk about anything specific there. But there the application is mostly group theory. But I still think like in the case of neural network, there should be something that we can say because I actually did see some papers discussing the loss landscape in terms of critical submanifolds and stuff. Um, so yeah, but anyway, these are just things things I know I can pull out on top of my head. But I even know some papers. I can probably send some papers um, in channel later.
Yeah, that would
But
be
yeah,
awesome.
these are all you can say.
Thanks. I think there's a question by Jimny. Maybe if you want to ask it in the voice chat.
Sorry, what?
There's a question by Jimny. He posted it in the chat, but maybe he wants to.
Right, let me see. Let me open it. Yeah. Describe topological aspects of things of neural network dynamics. Yeah. Lost landscapes. Exactly. That's I don't know any concrete results, but I feel like this should be something out there. I think it's possible. That's why I kind of want to bring it up here. I want to talk about Morse theory because I always vaguely feel like there's something. Um, and yes, the obstruction is that the Morse theory is sometimes kind of abstract, but we want to talk about something concrete. So um, yeah, again, I mean, we can try to read papers and maybe there's some inspirations. And specifically, I feel like there should be something from coming from singularity theory because they talk about the parameterizability and effective parameters and everything. I do feel like there's some parameters that are wasted and they kind of encoded in the way lost landscapes is formed, something like that, very vaguely. So, but concrete results, no, I don't know. Yeah, so
On
hopefully
the
that's
topic of singular learning theory, there's been like seminar session or seminar series on that, where they explain there's now a video series where they explain all the basics of it at least. So
Yeah, the less wrong, right?
No. I think by some of the same guys as that, they made like a conference, I think, about singular learning theory where they had sessions explaining the. Like, I've only watched the beginning, but it seemed very nice.
Oh, I see. So, that's a conference. That's a workshop you went to, right?
I haven't, but I saw the.
It's a different thing. Oh, okay. Sorry.
No. But yeah, so like singular learning theory has been getting some nice explainers, so we can probably cover that a little bit.
Yeah. Cool. All right. So. Okay. So if there's no question, that's it.
Okay, then yeah. Thank you so much for this.
Yeah.
Sorry. More question?
No, we were just thanking you.
Thank you. It was awesome.
Oh yeah. Okay. You're welcome.
Awesome. Thanks.